Assalamualaikum warahmatullahi wabarakatuh. We are from Group 9 and will present to you about one real-world application of solving differential equations using eigenvalues. Our group chose vibrations of the suspension bridge as a real-world application, and in this presentation, we will talk about definition, methodology, results and discussion, and conclusion related to this topic. So we move on to the definition first. Solving differential equations using eigenvalues is a powerful mathematical method that simplifies the analysis of complex dynamic systems. This technique is particularly effective for systems of linear differential equations, where the eigenvalues of the coefficient matrix reveal important properties about the system's behavior. Eigenvalues determine whether a system grows, decays, or oscillates over the time. A real-world example of this application is the analysis of suspension bridge vibrations. The motion of the bridge can be modeled by a system of linear differential equations derived from Newton's second law. In this context, eigenvalues represent the natural frequencies of vibration, crucial for understanding how the bridge responds to the external force like wind and traffic. Using this method, engineers can determine if a damping system is needed to minimize the maximum movement of the bridge and enhance its longitudinal stiffness to make it stable. This combination of theory and application highlights the importance of eigenvalue techniques in solving differential equations.
Okay, so I will be explaining the methodology we use to analyze bridge vibrations, focusing on eigenvalue analysis to identify natural frequency and modes of vibrations. Begin. To analyze vibration, we start with Newton's second law and continue with motion equation, and by combining both of them, we will get those two multiple equations for M1 and M2. Then we do amplitude, velocity, and acceleration, and are expressed as Z, W, S, and omega, since I don't find any omega symbols on the camera. And we substitute back in multiple masses equation, and we can see the equation as that. When we simplify using matrices, we let lambda equal to an omega square, which omega is natural frequency. Substitute it, and we can see lambda as an eigenvalue and v curly bracket as an eigenvector.
Hello everyone, I will be presenting the result and discussion focusing on the mode shapes and frequencies we analyze using eigenvalue method to understand bridge vibrations. Let's begin with the key findings. Eigenvalue analysis allows us to determine the natural frequencies and mode shapes of a structure like a bridge. These frequencies represent how the structure naturally vibrates, while the mode shapes show the pattern of deformation during vibration. For example, in our analysis, we identified three key nodes. Firstly, mode 1 at 3.2 Hz. This represents primary bending where the bridge moves like a single wave. Secondly, mode 2 at 6.8 Hz. This is torsional motion where the bridge twists. And lastly, mode 3 at 10.5 Hz, a higher order bending mode with more complex deformation. Now, let's look at the visual representation. The graph shows the mode shapes along the bridge line. For mode 1, which is the blue line, has a simple single curve pattern indicating primary bending. For mode 2, which is the green line, has two peaks and valleys representing the twisting motion. For mode 3, which is the red one, has even more peaks and valleys showing more intricate deformation as the frequency increases. These mode shapes help us identify stress point where the bridge experiences the most deformation. This is critical for determining where reinforcement are needed. So, why it is important? Understanding this vibrational characteristic has two major implications. Firstly, It will allow engineers to design safer bridges by avoiding resonance. For example, resonance occurs when external forces like wind or traffic match the bridge's natural frequencies, amplifying vibrations. Secondly, it will optimize material usage, ensuring the bridge is strong where it needs to be without unnecessary weight. However, there are also challenges. Real-world structures often involve damping and nonlinear behavior, which aren't always captured in simplified model. Additionally, analyzing more complex design increases in computational requirement. In conclusion, eigenvalue analysis plays a crucial role in modern engineering. By understanding a structure's natural frequencies and mode shapes, we can ensure its stability and longevity, avoiding failures like the infamous Tacoma Narrow Bridge collapse. Thank you.
Our newsreel, the actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases.
So we now arrive to the conclusion of this discussion. The vibrations of a suspension bridge offer a fascinating application of linear algebra in understanding complex physical systems. By modeling the motion with a system of linear differential equations, we translate the physical behavior into a mathematical framework. The coefficient matrix of the system plays a central role, as its eigenvalues reveal the natural frequencies of vibrations, critical for determining the bridge's stability and resonance behavior. Similarly, the corresponding eigenvectors represent the modes of vibrations, describing how structure deforms under specific frequencies. This relationship highlights the power of linear algebra in connecting abstract mathematical concepts to tangible physical phenomena. Through eigenvalues and eigenvectors, engineers can predict and mitigate potential risks, ensuring the safety and functionality of suspension bridges under various conditions. Linear algebra not only provides the tools to analyze such systems, but also bridges the gap between theoretical insight and practical engineering applications. That's all from us. Thank you.